Back. We're almost finished with chapter 3, and it will be the end of the quarter. So, very exciting times. And we're going to talk about solving conversion problems. And this is a skill that you will use for the rest of the year. So, this is something also very useful and fundamental, and something we're going to carry through. So, we're going to use a lot of conversion factors. We've already done that when we did our metric conversions. Now we're going to do all sorts of other conversions. So, for example, if they're 4 quarters and a dollar or 10 dimes, we can use any of those as a conversion factor. So I could say there are 20 nickels are equal to 100 pennies, and I could use that. Or I could say 5 pennies is equal to 1 nickel. So I have lots of conversion factors I can use. And whenever I use those, I can write them in a variety of ways. I could write either the centimeters on top in this example or centimeters on the bottom as on the right. In either case, they are equal to each other, and it is an equality that we're using that will help us convert things. So if I want to have, and as we talked about in class, whatever I have as my starting number, the next conversion factor has to have that unit in the bottom. And so that's how we can decide which ratios that we need for our conversion factors. The measurement in the numerator is the one that we're going to. The one in the bottom is the one that we already have. And so we're going to continue on. The figure illustrates above. Each of those are 1 meter long, but we are going to use either 100 centimeters or 1 meter, depending on which way we want our conversion factor to go. So they're useful in solving lots of problems because they're expressed in 2 different units, but they are equivalent in terms of value. So when a measurement is multiplied by a conversion factor, the numerical value is changed, but the actual size of the quantity measured remains the same. So if I have, and we don't use the DG, but if I have 1 gram, that's exactly the same as 100 centigrams, or 1 milliliter, or 1 liter is 1,000 milliliters. So they're the same thing, they're just expressed with a different unit. In addition, conversion factors within a system of measurement are defined quantities or exact quantities, and therefore they have an unlimited or an infinite number of significant figures, like we talked about when we did sig figs. They would not be used when rounding our number. So we have a conversion factor here that 1,000 grams equals 1 kilogram. So I could write it either as 1,000 grams divided by 1 kilogram or 1 kilogram divided by 1,000 grams. So here you can see on the scale of that picture that there's actually 2 different units being used, and you could use either. And so we're basically doing that kind of calculation. We're just converting it from one unit to another. We've talked about the metric system. So 1 times 10 to the 9th nanometers is equal to 1 meter, and we can use that as a conversion factor either way. We can also do the same thing with microliters to liters or liters to microliters. There's a lot of verbiage in here. What is the relationship between 2 components of a conversion factor? Well, they are the same measurements with different units. So the numbers look different, but they're actually measuring the same amount of a substance. What kind of problems can you solve? Now we're actually getting into what you need to know using dimensional analysis. And basically, almost all calculations in chemistry use dimensional analysis. And I will want you to do it the way I like it. So it's a way to analyze or solve a problem using units or dimensions of the measurements. And so it shows me how to step through a problem using those units as my guide. And we've already done this with metric conversion, so this really is not new. We will do a lot of these problems in class. You will be very comfortable with this by the time we take our test. So how many seconds are in a workday that lasts exactly 8 hours? So we have 8 hours. We know that in 1 hour there are 60 minutes, and in 1 minute there are 60 seconds. And so to figure out what we don't know, we're going to use dimensional analysis. So we have a number of conversion factors, but here's really the meat of the question. We're going to start with the 8 hours. And I would draw a line straight across, and this 8 hours would be right on the top. And once I have 8 hours here, I know that 1 hour has to go on the bottom and 60 minutes would go on the top. Since I have minutes on the top here, minutes have to go down here, seconds would go up here. Then since everything's on the top, I would multiply 8 times 60 times 60, and that gives me that many seconds are worked in an 8-hour day. And some days I feel every last one of them. That's a lot of seconds. So, does the answer make sense? It does. We have the right unit. It is a large number since we went from hours is a large unit to a small unit. Our number should get bigger. So, as you read sample problem 3.10, you'll see how the same problem could be solved algebraically, but it's more easily done with dimensional analysis, and I am going to require it. So, the directions for an experiment ask a student to measure out 1.8 grams of copper wire. The only copper wire available is a spool with a mass of 50 grams. How can a student do the experiment before the copper run? How many students can do the experiment before the copper runs out? So we have 50 grams. We want each student to have 1.84 grams of copper. How many students can we get to do the experiment? So we can say that for one student, I need 1.84 grams, or I need 1.84 grams for one student. And we'll decide which of these two conversion factors we need. So we're going to start with our 50 grams. And again, I would have a line straight across. My 50 grams would go on the top. And since I have grams on the top, grams have to go on the bottom. And then one student would go on the top. I want to come out in students, so that works out well. And since 50 divided by 1.84 gives me 27.174, and I cannot have a part of a student, so I can only get 27 students to complete the lab. So, if the exchange rate between dollars and euros is 0.7 euros for every dollar, what is the conversion factor that allows you to convert from US dollars to euros? Since I want to come out in euros, I would want that on the top of my conversion factor. And so it would be 0.7 euros for every $1. In chemistry, as in everyday life, we can use dimensional analysis to convert from one unit to another unit to make it easier for us to understand or know what we need to know. So I'm going to stop here and we'll start this in the second video. This is roughly halfway through. See you in a little bit.